Hello and welcome to the first video of the FP1 chapter Complex Numbers. On the screen, 5 quadratic equations to solve. Pause the video now and give this a go, but solve each one using a different method. This is leading into the concept we're going to talk about in this video. I'm going to do it on the screen just now. I'm going to start with this one. We can have x plus 5 and x minus 1. Which will give us x is equal to minus 5 or x is equal to 1. And here are our two real solutions. Next I'm going to do the one in the middle because it's got a coefficient of 1 on the x squared, which makes me think it will be easy to complete the square. So I'm going to take x and half of the b value, so a 1, square that, because I know that gives me x squared plus 2x. But it also gives me a 1, which I don't want, so I'm going to subtract 1 to get rid of that, and there's a minus 7 still that I do want. So that will be 8x plus 1 all squared, which gives me x is equal to, take the 1 on the other side after we square root 8, that's 2 root 2, plus or minus, and a minus 1 in front. Here again we have two real roots. Up to the top right, I'm going to now use the quadratic formula. Don't forget, in terms of an exam, you need to put the numbers in, because you're getting the mark not for writing the formula, but for applying the formula. So I'm going to go straight in with 9 plus or minus the square root of minus 9 squared, though because we're squaring it, that minus isn't all that important. Minus 4 times a times c, all of that is square rooted, and we divide it all by 2 times 2. And if you put that onto your calculator, you will get the answer of 9 plus or minus the square root of 33 divided by 4. Again, two real solutions. Down to the bottom left, here we have 5x squared minus 8x minus 11, and you might not consider this a separate method, but I'm going to just use my calculator. So on my calculator, I have a solve equations mode, put a 5 in, minus 8 for b, and minus 11 for c, and my calculator says that that is 4 plus or minus root 71 divided by 5. The least effective way to get marks in an exam, because you haven't shown a method. The last one, down on the right, I'm going to use a method that I also wouldn't be able to do in an exam very effectively, and that is using a graph. Because if you've paused the video to try these, you might have noticed already that we cannot solve this equation. If you put it on your calculator, either you'll get something that doesn't quite look right, which we're going to explore in this video, or you might get math error, depending on your calculator. And the graph shows why quite nicely. So here we have the graph of 2x squared plus 5x plus 6, and if you remember, the roots of this equation, when this equation equals 0, that's when the y-coordinate of the point on the graph is equal to 0, or effectively where it crosses the x-axis, and you can see why this has no real solutions, because it does not cross the x-axis. There is no solution on this graph that gives you a y equals 0 coordinate. And you might be used to writing this in a certain way. You might be used to writing it as no real roots. And that's a very good way of writing it because of this word real in the middle. There are no real roots to this equation, but there are still roots. This is part of what we're going to look at in this video. So to give you an overview of this chapter, we're going to understand and use imaginary and complex numbers, solving quadratic equations with real coefficients. These two are going to go together in this video. The next video we will look at multiplying complex numbers and also understanding and using complex conjugates. The reason they go together is because one use of complex conjugates is to divide complex numbers. Then we'll look at something called Argand diagrams, then modulus argument form, which comes out of Argand diagrams, and finally we will come back to solving equations that have complex roots, but we will take it beyond just quadratic equations. we'll extend this into other polynomials. So that's an overview of the chapter. Let's get going with imaginary and complex numbers. This video has a little bit more discussion in it because we are introducing a whole new concept, a new branch of mathematics. And it came about from this idea of the square root of a negative number. In that last starter question, the reason we couldn't get an answer out of the formula, the quadratic formula, is because you end up squaring a negative number, and we all know you can't do that. And that's an absolute fact. You cannot square root a negative number. What we're going to discuss in this video doesn't change that fact. You can't do it. There is no number that when you square it, you get a negative answer. Which is why these are called imaginary numbers. Now it might seem strange, but there was a point where someone said, even though we can't do this, let's still call it something. And he said, let's call it I for imaginary, because it doesn't exist. Another way of writing this is I squared is equal to -1. And the amazing thing was that this idea fits so nicely with all of the other mathematics that we have. You can make it work so that there aren't contradictions. You don't have to worry about, oh, this is a new thing, what happens if it doesn't work with the other stuff? It does. But obviously there are some rules in order to make it work, just as there are rules in ordinary mathematics. And as you go into negative numbers, for example, another concept that doesn't really exist in the real world as such, but does have meaning, just like imaginary numbers don't really exist, but they can have a meaning in the real world. We need to understand how negative numbers interact with positive numbers. In the same way, we need to understand how complex numbers or imaginary numbers interact with real numbers. So a few things to take down. If you're taking notes, write these down. Imaginary numbers are those numbers with no real part. For example, if you've got something like this, any given number that involves an I, this is an imaginary number. Real numbers, and hopefully you're familiar with this little symbol for real numbers, are those with no imaginary part. And obviously this is all of the numbers that you're used to in the maths that you've done from the first moment you did maths until this chapter. Complex numbers with this symbol combine these two ideas, because it's no good just throwing open a new branch of mathematics, inventing something new, if it doesn't work together with the stuff that's already there. So imaginary and real numbers need to be able to work together, and we call these complex numbers. And these have both a real part and an imaginary part. So this is the most general type of number. You can imagine this. Real numbers are a subset of complex numbers whose imaginary part is 0, and imaginary numbers are a subset of complex numbers whose real part is 0. And we write a complex number like this. It's got a real part and it's got an imaginary part, just like an algebraic expression. A little side note here is that with complex numbers, we more often use z, or sometimes w, instead of x, to represent a complex number variable. So if you see an equation that has a z in it, a mathematician would probably assume that this was a complex number. If you see an x, you're more likely to assume it's a real number. And they have the general form a plus bi, just like this, where a and b are defined as real numbers. Now that might sound strange because I've just said this is the imaginary part, but what I mean is the b by itself is a real number, and having the I attached to it makes this the imaginary part of the complex number. We do not have imaginary numbers within imaginary numbers. So this is a definition. If you've got a complex number with a real part and an imaginary part, the number here and the number in front of the coefficient of the I are real numbers. And we can call this the real part of z and the imaginary part of z. So the two parts of a complex number, the real and the imaginary, cannot be combined. Like I said, similar to an algebraic expression. However, again, similar to an algebraic expression, if you add two different algebraic expressions and they have like terms, you can put those like terms together. In the same way, if you've got two complex numbers being put together, you can put their real parts together and their imaginary parts together. You just can't put the real parts with the imaginary parts. So, for example, if we have z1 here and z2, and I want to add z1 plus z2, we have this equation here, and then I can put my two real parts, the 2 and the 3 together make a 5, and the 7i minus a 4i make a 3i. Nice and formally, you can rearrange it. Obviously, you don't need to write all of this out each time, but you know that these numbers are commutative, and this is what we get. You can also multiply complex numbers by a real number, just like expanding brackets. Again, z1 is 2 plus 7i, and if I want minus 6 times z1, I put that in, and I can do minus 6 times the real part, 2, to give me minus 12. Minus 6 times the 7 gives me minus 42i, and that's the imaginary part. And there you have most of the key ideas ready to do a few examples. So we have the square root of minus 36. Now this is equal to the square root of, if I'm going to be very clear about what is going on, minus 1 times 36, which you know we can then write as two separate square roots. And that gives us 6 from the square root 36 and an I from the square root of minus 1. Now if this was a plus minus in front of the original square root, then we would have plus minus here as well. That still applies. If there isn't, it's implied to be the positive root. You don't need to go through this every time though, obviously. So here we've got a minus inside the square root, so we're going to have an I, and then we just need to square root 28, which is 2 root 7. So we have 2 root 7 I. And it's convention to write the I at the end, which means I often put a little down tick on my square root to show where that finishes. The next set of examples are fairly straightforward. You can see here we've got 2 and 7, so the real part 9, the imaginary part 5 plus 3 gives 8i. All the usual algebraic rules apply. Here we have minus 3 and plus 6i because the minus 11. Here we're expanding to give 10 minus 16i. And here, again, to make it clear exactly what's going on, I will factorize first, doing the reverse of part C, and then of course that cancels, and you can see that just as with usual fractions, we have divided each of the two parts of our expression in the numerator by the denominator. That's the end of the simple examples. Let's go back now to quadratic equations. So now that we can square root a negative, any quadratic equation should always give you two solutions. Although, of course, sometimes it may be a repeated root and therefore appear only to be one solution. But you can never have no solutions anymore. Either you'll have two real solutions or complex solutions. So part A, we can just rearrange this. And we now know that the square root of minus 9 is 3i. So my two solutions are plus or minus 3i. For part B, I'm going to use the quadratic formula. So we have minus 6 plus or minus the square root of 36 minus 4 times 1 times 25, all divided by 2, which gives me minus 6 plus or minus the square root of minus 64 all over 2, which we now know can be written as 8i. And in its simplest form, that is minus 3 plus or minus 4i. And again, we have two complex solutions. Finally, part C. In an exam, you would solve this in the same way as part B, but in terms of contrasting it with our first 5 questions, I'm going to do this on my calculator. And my calculator, although it's forced to give me an x rather than a z, tells me the value 5 plus root 31i over 4. And of course the second result is minus in there. So my calculator will give me this result, and it will be quite obvious that it's a complex number because the I is simply there on the screen as an I. If your calculator does not do that, then be careful of using it. Either way, in the exam, you should of course show your process. And that should be enough for you now if you have a textbook with questions in it to do some of these exercises. In the Edexcel book, it is exercise 1A and 1B. And maybe I'll see you in the next video.